All right, cool. So we're recording. So let's begin. My name is Ketki. Today we are taking the first workshop on computer vision. And today we'll be focusing mostly on getting data for our image and video processing algorithms and understanding how images get converted into features, which is what we saw in the first two machine learning workshops, is that we need features and we need something to predict. So we'll be starting with what exactly is an image, like in the computer version, not just in the visual version, but in like how it gets converted into features and then how it's processed. So the libraries that we're using today are OpenCV, which is a very useful library. It's built in C++, so it's extremely fast. As we know, images and videos are like huge in size, so we need fast libraries to process them. And OpenCV is a very well established, and it's everywhere basically. And then we are also using NumPy and Matplotlib, which we saw in the previous workshops. So as we know, images and videos are made up of pixels, pixels are just like discrete picture elements, which you assign a value to them to display their color, to display their brightness, to display how the pixels should look up on the screen. On our screen, we usually just go with the coordinate system, which is known as the left-handed coordinate system, which is where your origin is the top left of your screen, and then your horizontal axis is your x-axis, and y is the vertical axis. These are some common image formats that we usually deal with in our daily lives. Of course, PNG and JPEG, everyone is familiar with. These are the most popular ones because PNG is optimized for storage. Other formats that you might come across are TIFF. There's also EPS, which is the file format that is output by Adobe Illustrator. Adobe Illustrator also outputs like .ai files, which are vector file formats. So a vector file format is one in which you can, stretch the image as much as you can, but it won't lose its how do you say? It won't. Sorry. The sharpness. Correct. Yeah. You can stretch it any way that you want, and the pixels won't lose their sharpness. And of course, raw format is one that is output by your DSLRs. So this is the most the rawest form of the video that you can have, and after that you process it to convert it into MPEG so that you can share it across different platforms. There are some references here which you can check out to understand more about how these mesh formats are different from each other. But for the purposes of this workshop, you don't really need to know how these are processed. We'll mostly be working with JPEGs and MPEGs. All right. So we understand color in a very different way than how computers understand color. So we need some model to convert our perception into computer understandable format. So the most basic color model that we have is the RGB color model, in which a pixel has 3 channels. So the 3 channels are red, green, and blue, and you specify values for these 3 channels so that you can, so if suppose that, so these pixels, they get values in from 0 to 255. So say that you give 255 for red, 0 for green, and 0 for blue, then the pixel will appear red. So based on that, you can mix and match these values to get different colors for the pixels. This is your basic like Art 101 color diagram, where if you mix red and blue, you get magenta, green and red, you get yellow. And then if you mix all of these together, you get white. So the RGB model is an additive model. What that means is it is trying to add colors to a black base. So it considers that the base of your computer screen or any screen is black, and then you add colors to it to get red, to get green. And if you add all the colors to it, all the 3 colors, then you get white. The complement to this is the CMYK color model, which stands for cyan, magenta, yellow, and key. The key represents black in this model. This is the subtractive model. So it starts with a white base, and then you subtract colors from it to get the color that you want. So for example, to get cyan, you would subtract magenta and yellow from it. And if you subtract all the colors from it, then you get black, which is your base. And the third model that is quite popular is the HSV color model or the HSL model, where H stands for hue. Hue is the shade that you want, like red, green, blue. Saturation is the, the range of grayness that you want in an image. And value is the brightness. So it's either value or lightness. So it becomes HSV or HSL. And, like in this diagram, you can see that if you go from value 0 to 1, then the image becomes brighter. Like 1 is the brightest that you can have and 0 is the darkest. Hue is defined by this angle here. So if you specify a 0-degree angle, then you get red. If you specify a 120-degree angle, then you get green. And then I believe 240 is for blue. Yeah, 240 is for blue. And this axis over here is the saturation axis, where you can specify how saturated you want the color to be. So if you specify a saturation of 0, it's going to be white. So here I'm just installing these libraries for us to use. I've commented these out because I've already installed them in my Colab. Importing the libraries. And then I uploaded an image to my Google Colab, and then I'll be using that image. So we'll be using OpenCV today. cv2.imread is the method that you use for importing your image into your Colab or your Python runtime. Just using this image today because it's quite pretty. And then we're using the imshow function. So this is an overloaded function. The actual cv2 function is cv2.imshow, but this has been known to be buggy and it crashes in Colab. It also crashes in Notebook sometimes, Jupyter Notebook. So, some people just came up with this alternative, and that's the one that we're using here to display this image. So our image is contained in this image_RGB data. One thing to note here is that we write here RGB because that's the convention that we used to, but OpenCV actually uses BGR instead. It's just a different way of saying the same thing, just the order is different. So what if you want to read the image in grayscale? Then you can use this property right here to specify that you want the image to be black and white, and we are reading that into this variable right here, image black and white data. Okay, so how are these, actually, what is actually RGB data? What is BW data? What kind of Python variable is it? So it's basically a NumPy array that we can see here. Its shape is, this 2012, 32, 20, and 3. So this first value is the height of the image, then the width, and the number of channels. Now, since the RGB image is RGB, that's why it has 3 channels, one each for red, green, and blue. And since we read the image using the black and white property, it has just one channel. And so that's not displayed right here. So it's just going to be height and width. And of course, it's represented in values between 0 and 255. So that's why the type of the data contained in the NumPy array is unsigned integer. And it's size 8 because, of course, like 2 raised to 8 is 256. So you can represent 0 to 255 using that. Okay, so what if you want to convert an image? Like, what if you don't want to read it, using that, the previous property that I mentioned? You can just use convert color to convert it into, into grayscale. You can also use, there are other options right here that I haven't used, but this is the most common one that you would use. And we're just, reading that image into RGB to gray. And it's the same thing as using the other. So this is just another option that you can use. Now we want to see, like we want to visualize like how the image, what the image distribution is basically, like how many pixels are in the red zone, how many are in the green zone. So for that, we can use a histogram. So as you know, a histogram is just a plot that displays, like what the distribution of the image internally is. So right here, I am creating a histogram from the RGB to gray image that we just read. And I've specified the bins as 256. So 256 means that for each of the values between 0 to 255, I want to find out how many pixels are in that value. So if I specified maybe like 128 here, then the bins would be like 0 to 1, 2 to 3. And whatever pixel has value 0 and 1, it would be in the same bin. So you just not get as as granular a histogram as you would with 256. And this is a range that I'm specifying for the pixel values, that my pixel values are only going to be between 0 to 255. So that's the histogram, and then I'm displaying it here. So as you can see, like 0 would be dark. Sorry, my bad. 0 would be white, and then 250, like 255 here would be black. So most of our images are somewhere in between, because you can see like about 70,000 to 80,000 pixels are in the like middle range. So the pixel is not too dark, not too bright, it's just somewhere in the middle. Now for the histogram of the RGB image, we can display different lines for each of the channels. So our image was pink, right? So a lot of the pixels have a large value for the red channel right here, and a large value for the blue channel. But a lot of the pixels have a very low value for the green channel, because there's not a lot of green in the image. So the values for the green channel are going to be, near bit like near 0, and they're going to be in the lower range. Often what we need to do is like try to equalize the image, because we don't want the image to be like concentrated in some areas. We don't want the pixels intensities to be concentrated in some areas. So we want to distribute those intensities over the image, so we can better visualize the image, and it's better for the algorithms to understand what the image actually is. So for that, we can use equalization. So this is kind of like normalization. How you would, for example, if you had some data, for example, say salaries. If you had salary data, and it's some values are in the very high range, some values are in the very, very low range, then it's going to be hard for the algorithm to understand, like the algorithm might not do well with that kind of range, because some predictions are going to be concentrated on the lower end, and some predictions will be concentrated on the higher end. So you want to normalize that scale, so that it does well with the test set as well. So that is kind of analogous to what we're doing here. We're equalizing and normalizing the pixel intensities, and you can see that we like almost immediately we get a better image that the algorithm can do better with, because as you can see here, like on the left hand side, some areas are too bright, and some areas are not as, there's not a lot of contrast here basically. On the other hand, on the right hand side, there's a lot of contrast, so the algorithm can decide what picture, what part of the image that it needs to focus on, so that it's not doing well on some parts of the image and doing badly on some other parts. So that's what this method right here is doing. It's taking this cumulative sum of the images, and then it's normalizing it with the maximum. So this is kind of like what you would do with like finding z-scores in your like normal integer data. This is the image equivalent of that. I'm just plotting those plots right here. Now some pre-processing that we sometimes want to do is image thresholding, whereas images are too large. So we don't want all that data here, all that data, all that huge amount of data, or that huge amount of range for the pixels. So what we can do is like try to find a threshold. For example, here the threshold that I'm using is 127. So the pixels that have intensities, less than 27, they're going to be thresholded to 0. And those pixels that have like a value greater than 127, they're going to be becoming 255. And so this is just another way of getting a huge contrast in your image. So as you can see here, like these bright parts, they just become zeros over here, and the darker regions, they become 1. Now, another transformation that you can do is inversion, where you just, like do the opposite, like the bright parts become 1s and the dark parts become zeros. And now we move on to a very central part of computer vision, which is convolution and filters. So often what we want to do is modify the pixels in such a way that the image that is output from that modification, it has lower size, or it has greater intensity. Whatever you want to do with the image, that's possible using filters. So what a filter basically is just a matrix of values like this right here. This is a 3x3 matrix. It's called a kernel. And we take our image and we slide the kernel over the image, and we multiply elements of our image with elements of our kernel, and we find out the addition of that whole part of the kernel. So let me explain that using this right here. Of course, it's gone. Okay. So this is our image right here, and the kernel that they're using right now, let's change it to, let's say, outline. Okay, so look at this kernel right here. Only the middle cell has a value of 8, and the rest of the cells have a value of -1. So what's going to happen is, if we take this part right here, see the multiplication that's happening. The top left pixel has a value of 35. We're multiplying it with -1. So this way we multiply each element of our image with each element of our matrix, and then we find out the sum. So this kernel outputs a sum of 6, and so that pixel on the right hand side gets that value. So that's how, because see, here what we're specifying is that our edges are not really important. We want a higher value for the middle element so that it becomes brighter, and then the edges, they become darker. Is that clear? Okay. So that's how, like the elements that will be the elements of the image that will be placed on this one, they're going to become darker, and this middle part is going to become brighter. So that's how you get an outline, because then you get that contrast between dark and bright. Let's see it with another one, maybe blur. Yeah, so see, for here, what they're specifying is the elements that are on the corner of our kernel, they're going to be the lightest, and the elements that are in this area, like this one right here, and then these, they're going to be a little bit darker. Oh, I said it the other way around. This is going to be this is going to be the elements that are there on the corners of these and are going to be lighter, and then this is going to be brighter. So that's how we get, we slide this. So we slide this filter over every pixel, and then we calculate new values for the pixel, and that's how we get the output image.
It's sort of like averaging, in the neighborhood, but you give more importance to exactly the center.
Mm-hmm.
But, because of the values around the center, it picks up a little bit of the features from around the neighborhood, and that's why it's called blurring, I guess.
Yeah. We can see another one right here, right Sobel. So this one, it's trying to darken the edges that are on the right hand side, and then brighten the edges that are on the left hand side. So that's why these values on the left are negative, and these are on the ones on the right are positive. So you can see that's the effect that's created right here. These are going to be brighter, and then the rest is going to be darker. So this is the function that we use for doing it in CV2. So in CV2, you don't need to do all these multiplications. You can just use this CV2.blur method, and it's going to apply your kernel to here. So this is, I've just created a widget. So you can slide your slider right here and you can, give it a second. So this is the kernel size that you specify. And the larger your kernel, the more blurred out is going to be. It's not working right now. All right, but it definitely works because I tried it. So maybe it's just not like doing it fast enough. So we saw Sobel detection, right? So this is the same kernel that that was used there. And if you want to do the left, if you want to do the top and bottom Sobel, so that's the kernel that you would use. And the net is slow or something. All right, we'll come back to that. Some other transformations that you can do is translation, flipping, rotation, resizing, cropping. So we have created some code here that you can do for that. So what we're doing right here is, why are these not executing? Is the Wi-Fi working?
Yeah, but I think it's just no.
All right. So this one right here, I've created this code for shifting the image up, and then I'm using roll to just like cut off some part of the image from the top and then attach it to the bottom. So that's what the roll is for. If you can see in the code right here, if the direction is up, then I'm slicing the image and then I'm appending it to the bottom of the image. It's very slow. And this is a code for flipping. So cv2.flip. I don't know what's wrong. Okay, my computer is frozen. Does yours connect to this system? It's like this is just not working.
Yeah, I guess it's fine.
Stop recording.
Yeah, I'm also having some problems, though. I mean, something was like displaying properly.
It's not displaying, right? Maybe the image is too big. Sorry, guys, you can take a 5-minute break while we figure this out. Okay. Mine is just like frozen.
Trying to